Alright, in this video we're looking at horizontally launched projectile practice problems. We've got, well, we did the first one in class. That was the projectile launched over the edge of the cliff. The cliff's 45 meters above the ground. That was, that's that. So I'm going to go to the next one. Brick thrown off a building at 10 meters per second. Here's my building. Here's my brick. Oh, why would someone do this? This is dangerous. Vx is 10 meters per second. It lands 50 meters away from the base of the building. So that's going to be, let's straighten this up. Come on. Come on. Let's have some accuracy here. Delta x is 50 meters. That's my horizontal displacement. There's my parabola, the trajectory, the flight path. How long did it take for it to reach the ground? How tall is the building? Here we go. Things we know about all projectiles: ax is 0, ay is little g. For horizontally launched projectiles, I know that the initial velocity in the y is 0 for all horizontally launched projectiles. Now we're going and listing stuff from the problem. Thrown from the top of the building at 10 meters per second. That's going to be my Vx. I don't need initial and final x because acceleration is 0. The velocity in the x direction is constant 10 meters per second. Delta x I know is 50 meters. And then what else is there? Time, don't know. And then v final y we don't know. Delta y we don't know. Time we don't know. So in this one I noticed that I have check, check, check. Things I know in the x direction, so that's where I'm going to start figuring out the rest of the pieces of the puzzle. I figure out what time is. I can put it over here. Then I can use time to figure out how tall is the building. That would be finding out my delta y. So let's start with the stuff in the x direction that we know and calculate time. I can use this guy. Delta x equals vxt plus 1/2 ax t squared. This whole term goes to 0 because ax is 0. 1/2 times 0 times t squared is 0. So range for projectiles is always just velocity in the x times time. Do we know delta x? We do. Do we know velocity? We do. So we're looking for time here, so let's isolate t. Let's substitute 50 meters over 10 meters per second. So we get 5 seconds is time. There we go. And go into our chart on both sides. So that was A, how long did it take for the brick to reach the ground? How tall is the building is now solving for delta y right here. So we have acceleration, initial velocity, we want delta y, and we have time. That points us to this equation. I'm calling down the positive direction now. With all horizontal projectiles, I call down the positive direction because its only motion vertically is downward. You can call it negative though. Just be careful that you make sure that your displacement would also be negative and your g would be a negative value. Initial velocity in y is 0, so this is 0. So simplify. Delta y is 1/2 gt squared, and when I'm solving for delta y, so I've got no rearranging here. I'm just substituting 1/2 10 5 squared is 125 meters, right? 5 times 25. 5 times 25 is 125. All right, those are the two pieces of that one. Then we're off to the airplane. All right, an airplane moves horizontally with a constant velocity of 115 meters per second and an altitude of 1050 meters. The directions to the right and upward have been chosen as the positive directions. Okay, if you're going to force me. So this one we're calling down the negative direction. Down is the negative direction in this one. Okay, and what else do we know? The plane releases a care package that falls to the ground along a curved trajectory, ignoring air resistance to determine the time required for the package to hit the ground, and then the other stuff. So this is horizontally launched. Notice that our altitude is our delta y here. That's 1,050 meters. Here is our delta x, the displacement or range of this horizontally launched care package. We have some other pieces of information. They already gave us the altitude over here. We see our velocity in the x direction is 115. So let's make a little chart for our stuff. Things we know about all projectiles: ax is 0, ay is little g. In this case, that's going to be minus 10 meters per second squared because we're calling down negative. It's horizontally launched, so initial velocity in the y direction is 0. Delta y is minus 1050 because it's downward is negative and its vertical displacement is downward. V final in the y, we don't know. Time, we don't know. In the x direction, delta x is unknown. Velocity in the x direction is a positive 115 because to the right is the positive direction. And time, we don't know. But if we get time, then we get to use it interchangeably in both dimensions. So that's what we're going to go after. We look and we see what we have, and we're determining time required for it to hit the ground. That's the first thing to do. So we've got this, 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 and we're looking for time. So we're going to look at our y dimension stuff. This is our equation where we can get fall time for our projectiles. Which way? So I usually write this minus 1/2 gt squared. So that minus sign in front of the 10, that's taken care of right there with my minus sign. So I just put in for g 10. I've already put in my minus sign for that value. Delta y is still going to be my minus 1050. Initial velocity in the y direction is 0, so this whole term is 0, just like with all the other horizontally launched projectiles. So delta y is minus 1/2 gt squared. So I'm going to multiply by a negative 2, divide by g, take the square root, and I get t. So there's fall time for any horizontally launched projectile. This one we got minuses in there because we're calling down the negative direction. So minus 2 times minus 1050 over little g is, or let's just put 10 in because we're substituting, is time. And so I have turn on, square root minus 2 times minus 1050 divided by 10. I have 14.49. 14.49 seconds is time. All right, notice again, this is the minus that's as a result of calling down negative, and that's the minus from little g, and here's the minus from delta y. You could do it by, you could call this a plus up here, you could do that, but then you'd have to make sure to put your minus down here in the denominator when you substitute in little g. Either way works, or just call down the positive direction. All right, so there's the time, 14.49 seconds. I can put that in my chart. 14.49, 14.49. All right, now we're off to find the horizontal displacement. Horizontal distance the package travels, so that's delta x. That's down here. All right, so looking at delta x, now that I have the time, here's my full equation, but acceleration in the x is 0, so that whole term is 0, so I have velocity in the x times time. We're looking for delta x, the horizontal distance, so the velocity in the x direction is 115 meters per second, and time is 14.49 seconds. So we have 115 times 14.49 is a big number, 1666.35. It's in meters. Do meters per second times seconds. So there's our horizontal distance the package travels. Next, we're looking at final velocity in the y direction, which is going to be, look at our final velocities right at impact in this one. So there's v final y, and in red horizontally, that's going to be v final x, because the acceleration is 0, it's still 115 meters per second. Velocity in the x direction doesn't change. And we need to find out that green value. So we look at what we have in our y column, our vertical column, and we have everything figured out. So you choose whatever equation you want to use. I guess I can just use this one. So it's just gt, because initial velocity in the y direction is 0. So v final in the y is going to be minus 10 times 14.49 seconds. V final y is minus 44.9 meters per second. Okay, so I know the final velocity in the y direction now. So I'm going to add that to my picture. If I'd like, minus 144 point, what was it? Just, 0.9, yeah. All right, so the last part of the question is, what is the total velocity on impact? And that's the addition of those two vectors in the horizontal and vertical direction. So you get the total velocity. How fast things actually moving. If it's got a speedometer on this care package, the speedometer is reading the purple line, the total velocity. We just break them down into their horizontal and vertical components or parts in order to do all of the analysis of the projectile motion. So the package's final total velocity is going to be the addition of those two vectors. And I need to get the magnitude and the direction. So this is the last part. If I want to find, let's say it's V final, that's a vector, that's an arrow on top of it. That's going to be the addition of V final in the y direction, that's a vector, plus V final in the x direction, that's a vector. Now this is always Vx the whole time. That's the one that's not changing. And since they're vectors, the way we're going to add them is with the Pythagorean theorem. So V final, its magnitude, I'm going to have to figure out its direction using an arc function, is going to be square root V final y squared plus V final x squared. So this is just Pythagorean theorem. So we have square root minus 144.9 squared plus, what was the other one? 115. Check back in my chart. Vx is 115. Having the XY chart is good just because you also don't have to go reread the problem if you forget a value. V final has whatever this is. So we've got 144.9 squared plus 115 squared. And then I got 34,222. Square root of that is 184.99. 0.99 meters per second. Quick check, that should be larger than either of the other sides of that triangle because this is not a hypotenuse, so it is larger, so most likely hit my buttons correctly on the calculator. There's the total final velocity. I also want to give the direction, so that would be the angle. So I could give this angle right there, call it theta. So that would be, I would say that's going to be its angle below the horizontal because it's below the horizontal. You could also call it the negative, whatever this angle is, because 0 degrees is measured from right here. There's 0 degrees. So if I want to find this angle, I can take, here's my opposite side is my V final y. My adjacent side is in red. So to get that angle value, theta is, let's use arctangent. Opposite side is V final y. Adjacent side is V final x. So theta is arctan. V final in the y was 1. If I use the minus, see, I don't use the minuses for the tangent. You got to be careful with the tangent. But you can just get the value of the angle using the magnitudes of the vectors. That's just what I always do. 115. And we're coming up here. Theta is, so we got to use our arctangent. I'm going to bring up my actual calculator. If I can find it. It's real quick. Edit this. Okay, there we go. So we're doing arctangent, so that's tangent minus 1. 144.9 over 115. 51.56. I check and make sure. I never know with this one. Yeah, make sure you're in degree mode. If you're using degrees, 51.56, 51.56, 51.56, 51.56 degrees. Wait to see if that makes sense. So which one of these values is larger? 144.9. This is the longer value, so I should have an angle here for theta that's larger than 45 degrees. I do. Looks like I've done a decent job. So I would give the direction of that purple vector the final velocity, where was it? Here we go. We would say it's 184.99 meters per second at minus 50, oh dear, 1.56 degrees. So the negative indicates that it's measured down into the fourth quadrant. All right, there's our airplane. What's next? Hot Wheels car speeds towards the edge of a horizontal tabletop. Hot Wheels car leaves tabletop with the velocity of 8. The table is 80 centimeters above the ground. How much time? All right, so this is starting to get repetitive, right? How much time does it spend in the air? This much. Square root twice the height, or delta y, over little g. Do I have to derive it every time? No, I don't have time for that. Table is 0.8 meters, right? Be careful, please. Be careful. That's 0.8 meters. G is, we're calling it 10. The magnitude of it is 10 meters per second squared. So make sure you're not doing centimeters twice 80 over little g. You're going to get some long time. And think about the time value that you get. Is it reasonable before, you know, a table of this height? Should be less than a second. So I've got square root. Oh, I got my calculator out over here now. Square root twice the height, 2 times 0.8 over 10 for little g, is 0.4 seconds. All right. How far away from the base of the table does the car land? We've seen this already. Do I need to write out the whole chart and do everything? At this point, it's just this. All right, we know it's plus 1/2 axt squared, but ax is 0. Ay is a little g. All right, you go and make that chart over there if you want. It's good to keep it organized. How far away from the base of the table is the delta x? Velocity in the x direction is 8 meters per second. That's how fast it's leaving the table. I know the time. It's 0.4 seconds. We're solving for delta x, so I have 8 times 0.4 seconds. So 8 times 0.4, that's 0.8 times 4, which is 3.2, right? 8 times 0.4 is 3.2. Yes, 3.2, obviously. And that's meters, because I used meters per second and seconds. All right, so that's how far away from the base of the table. What is the Hot Wheel car's total velocity right as it impacts the ground? All right, so if I have a little sketch here, this is just like the airplane. The car leaves with this velocity of 8 meters per second. It's going to strike the ground, and when it strikes the ground, it's going to have a final velocity in the y direction, and it's going to continue with this 8 meters per second in the x direction, call it v final x. And so to get the total, we need to know the value of that hypotenuse, and so I need to figure out v final y. It's a horizontally launched projectile, so remember, among the other things that we know, v initial in the y direction is 0. So this becomes v final y equals minus gt, which is minus 10 times, what did we say, 0.4 seconds? So v final y is minus 4 meters per second. The minus shows us that the direction is downwards, so I'm calling down the negative direction in this guy. So what is its total velocity right at impact? Now we need to get total v final, which I'm using purple for. So v final, its magnitude now, this doesn't tell me the direction yet, is square root v final in the y squared plus v final in the x direction squared. I'm just doing Pythagorean theorem again. So I have square root 4 squared plus 8 squared. So that's square root, what's 16 plus 64? Square root 78, right? 60, why am I even checking this? 16 and 64 is not 78. It's 80. 78. That's ridiculous. All right. So square root, I'm just going to put the whole thing in. 4 squared plus 8 squared. Square root 80, so it should be almost 9. 8.9. Say 8.94. Why not? Meters per second. And then we want to get our angle, which is going to be theta right there. So I'm using I'll use my arc tangent again. So tangent minus 1 of, opposite side is v final in the y direction, that's my 4, over my adjacent side is in red, 8. What is that? Half the value? Tangent 1/2. Why don't I know that off the top of my head? Come on. 26.56. That's why, because that's not really all that normal. I think it was 26.57. We round it. Okay, so it's 8.94. So total V final, I don't need the absolute value bars because now I'm saying the total vector with magnitude, 8.94 meters per second, and direction at, and this is going to be minus 26.57 degrees because it's below the horizontal. And it's below the horizontal negative angle. I should also correct this over here. There should not be absolute value bars if I have magnitude and direction. That's the full vector. All right, so there's our full vector, 8.94 at minus 26.57. We check the angle. Which one's the larger? The horizontal piece in red is larger, so this is not drawn to scale. So that means that our angle should be less than 45 degrees. It is, and 8.94 is larger than 4 and 8. So that's good. Last one. An ice cube escapes, slides across the cafeteria table, leaves the table, flies horizontally. The table's 65 centimeters above the ground. Okay, you notice the ice cube lands exactly 1 meter away from the base of the table, so this is 1 meter. That's where it's landing. How fast was it traveling when it left the table? All right, so we don't know the velocity in the x direction, which is its initial velocity when it leaves the table. All we know are our heights and the other stuff that we normally know about horizontally launched projectiles. So we've got ax is 0, ay is g, initial velocity in the y is 0. In this case, we know our delta y. I'm going to call down positive. I always call down positive for horizontal projectile. Delta y is, I'm going to write it in meters, 0.65, because g is in meters per second squared. Be careful. V final y, we don't know. Time, we don't know. Delta x, we know, is 1 meter. And I do not know the velocity in the x direction, and I do not know time. All right, so look for the stuff that we know. We know that, we know that, we know that. So we're using those 3 values to determine a 4th value. We make it time, then we can put time in both columns. Same dealio. All right, so we're going straight to finding time. So what is the time? Square root twice the height, or delta y, over little g. So we have square root 2 times 0.65 over 10. So I have 1.3 over the square root. Oh wait, my calculator's on the computer again. Sorry, I keep forgetting. Square root 2 times 0.65 over 10. Close parentheses. Is 0.36 seconds. How tall was this? About 65 centimeters? Okay. So that makes sense. It's a reasonable time, less than a second. And then we're going back to, fill these in on your chart, 0.36. And now I'm looking for delta x, velocity in the x direction. How fast was the ice cube traveling when it left the table? So here's the full equation once more. Oh, it's getting a bit redundant. Acceleration in the x direction is 0, so that goes away. So delta x is vxt, and we want to find velocity in the x, so please isolate stuff. And then delta x is 1 meter, and time is 0.36 seconds So what is that? It's going to be a little more than 3. It's 10th. Yeah. All right. So what? Yeah. What is that exactly? 1 over 0.36. A little less than 3. Okay. So 2.78 if we round it meters per second. It's velocity x. Okay. I think those were all of the horizontally launched ones. See, that's not much. I don't think there's much. You can tell that the major issues are like, well, identifying what the variables actually represent. You know, if you're given 2 different distances, make sure you're reading the problem properly. You can understand like distance away from the base of the table is this horizontal distance, and the height or altitude, like these are things that are delta y's. To make sure you first identify those variables properly. Then frequently you're using this guy. If it's horizontally launched, that's the time to hit the ground, twice the height. And here the height is the delta y. All right, but that needs to be the height that the object is traveling vertically. All right, that's everything.